Hello everyone, welcome to Chapter 3, Derivatives. Here we look at implicit differentiation. Just in English, implicit means something that's hidden, something that's not direct or straightforward. And differentiation, we saw, was the process of finding the derivative. To explain the concept here, let's begin by looking at this equation, y equals 3x minus 5. We can say that this equation is solved for y. What that means is that y is by itself. Y is isolated on one side of the equation, and the rest of the equation on the other side is written in terms of x. So if we were asked to find the derivative of y with respect to x, then all we do is do the dy over dx on the left side, and on the right side we come immediately to understand that the whole expression on the right side is to do with x, the one with respect to which we are trying to derive. Therefore, using the differentiation rules, we're able to simply come up with a 3 as the answer for this, isn't it? So we had no problem because it was all very open. It was very straightforward. You just had to differentiate the left side and the right side by simply getting your answers directly. So this is what we call as explicit differentiation. No problem, and we got the answer directly as dy over dx. So, in other words, I would just like to say explicitly would mean to get it directly. If I were to rewrite this expression, say as 3x minus y equals 5. It's the same equation, but I've rewritten this. Here, equation is not solved for y. Therefore, when I say find dy over dx, what we have to do is we have to either rewrite this whole thing in terms of y, or we'll have to derive them one by one, bearing in mind that only the x is derived with respect to x, but the y will have to remain as dy over dx. So what I mean is, if you took the derivative here, derivative of 3x with respect to x would be just a 3, minus derivative of y with respect to x will be dy over dx. And 5 with respect to x, 0, because there's no x there. And then we have to clean this up and isolate dy over dx on one side of the equation. So in other words, if I add dy over dx on both sides, I get 3 equals dy over dx. The same answer we got above, but it took us a while to get this because we did not do this directly. We had to do it indirectly. So we call this process as implicit differentiation. In other words, implicit would mean indirect. So you might think, we got the same answers essentially because they were the same equations. So why not we solve for y in the first case, like in the first case, so why not solve the second part as in terms of y and then find the dy over dx? Well, we can do that if the equations came as simple as this. Unfortunately, we have some other functions, I shouldn't say functions, there are some other curves that are not, that are not functions, which means they cannot be written explicitly as y in terms of x. So I can give you an example here. Now take a look at this graph. Is this a function? To answer that question, you have to perform the vertical line test. So drop vertical lines throughout the graph and you realize that the vertical line crosses at 2 points. In fact, we do have this one vertical line, could be seen as one of the lines in the vertical line test perhaps. And you see that you have 3 points through which that line passes, which means it is not a function. This is not a function, but it is a useful curve. It's got its own equation. But if you look at this curve, if you want to look at this curve as a function, then what we have to do is we'll have to split this up into 3 parts. The red part, as you see here, then the blue part, and then the yellow part. So each part, when you do the vertical line test, it passes. But if you did keep the function as it is, we would not have a function. So the entire curve is written like this. The equation of the curve, I should say. The equation of the curve is x cubed plus y cubed minus 9xy equals 0. Look at that. If I split them up as functions, I should be able to describe that function. You have that equation here, right? If I split this up, I should be able to describe what this red piece alone would be. Then I could write it as a piecewise function, one for the red, one for the blue, and one for the yellow. And then mark their own domains, right, over which this will work. And that looks cumbersome because without help, we can't really do that. So in these cases, if you wanted, or if you argued and said, well, like in the example I showed you previously, we can rewrite the whole equation in terms of y, or in other words, solve the equation for y and then find dy over dx. Won't that be easy? Look at this equation. Can you get y by itself? That's going to be super hard because you have the y cubed and you have this y term. It's not just the y cubed. If it was just y cubed and this was just a 9x instead of 9xy, perhaps that's possible, right? It'll be a cube root expression, but that's okay. But this one, you cannot isolate y as it is. Therefore, the importance of implicit differentiation. So you will have to differentiate this implicitly like this. You'll have to right, because you're differentiating with respect to x. X is the variable. So that will be 3x squared because that's directly x. But this one is y. So you'll have to say 3y squared, the chain rule, right? So 3 is the power. That's outside. This is inside. I say inside because y is not x. So you cannot directly get it. So 3y squared and times the derivative of y is dy over dx, the very thing we're trying to find. Minus 9xy. You have the chain rule there, and so you have the u and the v. So u prime v plus v prime times u equals 0. Can you see that? So here we are again not trying to collect all the y's, but we're collecting all the dy over dx. If you come back here, we said isolate dy over dx because that's what we're trying to find. In the differentiation, we're interested in dy over dx. Okay. So this curve is actually known as the folium. That's the name for it. Looks like a leaf, right? Like a flower. So this folium, which was actually figured out by Descartes. So a great mathematician. We have in cases of folium where it's not a function but it's a useful curve, we do have this situation where implicit differentiation will help us to collect these terms that contain the dy over dx and isolate dy over dx, which is done fairly manageably as opposed to solving for y and then finding the derivative of y, which is going to be almost impossible in this case, meaning you just want to do things the easier way. You don't have to complicate things, and implicit differentiation allows you to do it in the easier way. So you are indirectly finding dy over dx for a complicated expression like this, where y cannot be solved for. You've not seen folium before, so I understand that. What about this one? You've seen this before, right? This graph is nothing but your parabola sitting sideways, right? This is your parabola that's sideways. So this is basically, now let me write this here. Y equals x squared is your parabola that opens up like this, isn't it? So this is the inverse of that. That's what I'm saying. Inverse. Inverse means the x and the y positions will get switched. So y is now x and x is now y. So the equation for this one is x equals y squared. That's why it's sitting sideways. Now, is this a function? Once again, drop the vertical line test and you clearly see that this is not a function because it crosses at 2 points. Actually, you can see that. Because it's not a function, our challenge here is that we have to either split this up as the upper half and the lower half, so that because of the symmetry, the top part alone can be written as a function and the bottom part alone can be written as a separate function, so that they will pass the vertical line test. And that's what we see here. Here it's kind of easy in the sense that you can solve for y, isn't it? So that will be plus or minus square root of x, which will be y. And so the plus square root of x will be the top part, and the bottom part will be the negative square root of x. Are we there? So this was an easy case where the equation was manageable, so you were able to write it, and then you could find the dy over dx separately. But again, why go through all that trouble? Why do all those extra steps? Because all you have to do then is keep it as it is, right? X equals y squared is what you're given, and find the derivative. So derivative of this x will be 1 equals derivative of y squared. Remember the chain rule or the power rule. 2y times dy over dx. If we just call, if y, okay, let me put it this way. If it was x squared, we call it the power rule because you do 2x power 1, right? You don't do the times dx over dx because dx over dx actually is equal to 1. But if it is y, it is not the x itself. So when you do the power rule like you did for the x squared, the power rule actually becomes chain rule because you now have to insert the dy over dx. So that is the difference when you differentiate with respect to x, with x in the picture versus y in the picture. And then when you solve this for dy over dx would be 1 over 2y. Right? What you see then is now dy over dx contains an answer which is written in y. And that is acceptable. If it was explicit differentiation, there was no need for the y to be there because we were able to get y by itself. But because of the situation here, we do not have the ability to get y by itself. Therefore, we are only focusing on getting dy over dx by itself so that the answer will contain a combination of x's and y's or just the y or just the x. It just depends on the kind of equation we are faced with. There's another common curve that we like to use, which is not a function, which is this, a circle, right? We all love the circle. But you know the circle is not a function because, again, when you do the vertical line test, it fails. So what is the actual equation of a circle? In this case, the equation, it's a circle with center 0, 0 and radius 5, as you can see. So when we write the equation of a circle, it will be x squared plus y squared equals r squared. Because the center is the origin, you don't have the h and the k that usually comes in the equation. It's 0, 0. So x squared plus y squared equals 25 r squared. So clearly this is an implicit version, I should say implicit equation here, okay? Because you didn't get y by itself. But here again, because the vertical line test fails, you can split this up as the upper semicircle and the lower semicircle and get their functions separately. Here too, solving for y is kind of easy because y squared is 25 minus x squared, and therefore y is plus or minus square root of 25 minus x squared. Right? Again, the plus square root of 25 minus x squared will be the top part, as you can see, and the minus portion of it will be the bottom part. So we can write the y by itself and then find the derivative. But why should we do that? We don't really have to do that if we can simply do the implicit differentiation. So here again, you you're deriving with respect to x always. Keep that in mind. Therefore, derivative of x squared will be just 2x. But derivative of y squared will be 2y times dy over dx because y is a function of x. It's not x itself, right? And then this one, 25, derivative of a constant is 0. Then you can get dy over dx. Subtract 2x on both sides and then divide by 2y. So that gives us basically negative x over y. So here is a case where dy over dx has an answer that involves x and y. And that is the new way we look at things now in implicit differentiation, where it allows room for your answer not to be just in x, but in x and in y. All right. So I'm going to put up rules of implicit differentiation, meaning what steps to follow. What I just said is what I'm going to write as steps, and then we'll look at some examples. So here we have the two steps. First, differentiate both sides of the equation with respect to x, treating y as a differentiable function of x. That's a big deal. Meaning, when I say differentiable function of x, your y, when you differentiate y should be dy over dx. The second step is to collect all the terms with dy over dx on one side of the equation and solve for it. Okay. We'll do some examples so you get the hang of it. And we have y squared equals x squared plus sine xy. This is what we have, and we need to find the derivative. So if you look at the first step, it said differentiate both sides of the equation with respect to x. So I just say differentiate both sides with respect to x. So if you look at the left side, it says treating y as a differentiable function of x. So that's going to be the chain rule. So 2y times derivative of the inside, which is dy over dx. And then x squared, 2x. In fact, here also you can actually think of the chain rule, right, as I explained before. So if you did the derivative of the inside, you get dx over dx, which is 1. That's the reason why we don't do it for x, because that will always be the case. Okay. So it's enough that we just did the 2x. And then here you have sine xy. Remember that you have to apply the chain rule because you have the sine, which is the outside, and xy, which is inside. And so when you do the outside, you do the derivative for sine, which is cosine. But when you take the derivative of the inside, you have to do the xy as product rule. U prime v plus v prime u. That's what I'm going to do here. So it's cosine xy times u prime v plus v prime u. Okay. Please watch closely there. It's quite important we understand that chain rule and the product rule happening there. Let me put them all together. 2y dy over dx equals 2x plus, I'm going to throw this in the front, okay? Y plus x dy over dx times cosine xy. Please put all the parentheses around them so you can be very clear there. All right, so that was step 1. Let's go to step 2. Step 2 says collect the terms with dy over dx on one side of the equation and solve for dy over dx. Okay, so the next step for me is to distribute this cosine xy with these two terms so that I can get the terms separated. That will allow me to collect all the dy over dx together. So the left side, I write it as it is, 2x plus y cosine xy plus x dy over dx cosine xy. Are you with me on this? So we'll use the distribution there. Now our focus is on the terms that contain dy over dx. So let me just maybe circle the dy over dx terms. These are the only two terms that contain the dy over dx, right? So I'm going to collect them all on one side, and I prefer to collect them on the left side. So that means I will subtract x dy over dx cosine xy on both sides. Agreed? That means this will go away. On the left side, the whole purpose of collecting them together is to gather the dy over dx. So quite obviously, the dy over dx is the common factor in both these terms on the left. So pull out the dy over dx that is common to both, so that you're left with a 2y from the first term minus x times cosine xy. That's your left side. And on the right side, we have 2x plus y cosine xy. The other term cancelled off, so you just have this. And in step 2, if you come back here, it said collect the terms with dy over dx. We did that on one side of the equation. And solve for dy over dx. To solve means to isolate. So solve for dy over dx. Isolate dy over dx on one side of the equation. Right? We know that that's the language. So, usually your notes or even my instructions in future would not be constantly indicating to isolate. When I say solve for dy over dx, it means that you're asked to isolate dy over dx on one side by itself. All right, I will have to rewrite this step to show that action there. So I'll just repeat this step here. Okay, in order to get dy by dx by itself, I have to divide this out, right? 2y minus x cosine xy, this needs to be divided out on both sides, of course. So that this whole thing, this factor and this factor cancels off. We know that we cannot single out any term there because of the minus. Okay, only if it's a complete product can you individually cancel common terms. But here, this whole factor, this whole expression is one factor. And so if they match exactly, they're identical, yes, we can do that. And that's what we're doing to get dy by dx isolated. And that, my friends, is our implicit differentiation technique to get the derivative of y with respect to x. And that looks beautiful. Well, we do understand that it contains x and y in the expression, which was not seen before. So, in fact, it's one of the telling signs that we did perform implicit differentiation. Only then you have that, complicated mix of x and y on one side. Let's do another one. Okay. Kind of similar to the previous problem, so good time to do it on your own. Okay, so take the derivative, so differentiate with respect to x on both sides. How do I know to differentiate with respect to x? Well, obviously you have the x and the y and so familiar with this, but I always go by what they want of me by looking at this part of the question. Okay, it can be sometimes explicitly stated, or it could be given to us in a notational form like this. So we know that they want us to differentiate with respect to x. What is in the bottom is what we are trying to differentiate with respect to. So we got that. So 2 times, that's x times y. So it's product rule. So u prime v plus v prime u. That's there. Then y squared will be the chain rule. 2y times derivative of the outside times derivative of the inside equals x. Derivative of x is 1 plus derivative of y is dy over dx. We know in our minds that we're going to collect all the terms with dy over dx, but for that, let's first distribute. And the only place where I see the need to distribute is here. Right? All other terms are pretty much by themselves. That will be 2y plus 2x dy over dx plus 2y dy over dx equals 1 plus dy over dx. Now let's go up to the terms that contain the dy over dx. Just to help us with that, and circling only the dy over dx, that you know you're going to collect the whole term. What I'm thinking of is doing a two-way switch. So I'm going to subtract dy over dx on both sides so that I can collect them all on the left. And I'm going to subtract 2y at the same time so that I can move the 2y to the right. So I am basically trying to bring this to the left and move this to the right. Yeah? That will be 2x dy over dx. Write that properly. Plus 2y dy over dx minus dy over dx equals 1 minus 2y, because I'm subtracting 2y on both sides. I'm subtracting dy over dx on both sides. Very nice. Now I can factor out the dy over dx. It's 2x plus 2y minus 1 equals 1 minus 2y. One last step is to isolate or solve for dy over dx. So divide by this entire factor on both sides. Yes. Now this is very interesting, and it's there's this comfortable monotony here. But remember again, all this is the same concept of the slope of the tangent line or slope of the curve at a point. So what really is helpful here is, or rather I should say, why it doesn't bother us to have the x and the y is that if we have the point, right? If I want to find the slope or the derivative at a particular point, let's say 2, 3. The x will be the 2 and the y will be the 3. I have to plug in for x as 2 and y as 3 in this expression. And I would get a numerical value, the slope of the curve at that point. In fact, I can make my point going back to, yes, right here. You know, I found the dy over dx, right? So if I were to find dy over dx at the point 3, negative 4, let's say, that means my 3 is x and my negative 4 is y, right? So in my derivative formula, I'll have to have negative and then x is 3 over y, which is negative 4, which is 3 over 4. It's a positive slope. Can you see that information right here? So at 3, negative 4, the slope is 3 over 4, positive 3 over 4. And you can see that that's the slope of that tangent line. And I can fix any point. And what's really neat is that this will work for any point on this circle. So I could choose a point from the first quadrant or the third quadrant, doesn't matter, because I will get a corresponding slope. And for instance, if it is the second quadrant, the slope will be positive. But if it was the first or the third quadrant, I'll get a negative slope, right? And I can prove that point here. So let's say this was, say, 3, 4. If it was 3, 4, I'll have the slope right there. Negative 3 over 4, because x is 3 and y is 4. So you see that that's a negative slope, and you can see that the line is falling. It's a negative slope. So that is the whole focus of using, oops, I'm so sorry. That's the focus of using the implicit differentiation so that you could have the slope that can be found at any point, slope of the curve at any point. And so the implicit differentiation is such a big help because we can use this across the entire function and just, choose a point and you get the slope at that point. That is quite powerful. Here's the next question. Look at this one. This, usually we have y equals secant x, right? But here it's the other way around, x equals secant y. So you can clearly see that this is an inverse function, right? Where the x and the y are interchanged. Doesn't matter. We know how to get the derivative. So x equals secant y, and we know we have to differentiate with respect to x. So the derivative of x is 1. The derivative of secant is secant x tan x. But here it's not the x but the y. And remember, because y is in turn a function of x, we have to use the chain rule. So derivative of the outside times derivative of the inside. Derivative of the outside is secant, so that's going to be secant y tan y times derivative of the inside, which is the y, dy over dx. And it's been a long time since I wrote this explicitly outside, so I'll just write this as derivative of the outside, derivative of the inside. Now we need to get dy over dx by itself. So 1 equals, of course, divide both sides by secant y tan y, which is what we need to get rid of to get dy over dx. In this case, it's already on the right side, so you don't have the need to bring it to the left. This whole thing goes away. And we have, I can write it on the left because it's an equation. Doesn't matter which is on which side. You can leave it like this, or because these are reciprocal functions, you can say cosine y times cotangent y. Cozy coti. Look at the next one. Okay. Again, remember product rule, and within it we have the chain rule. Okay, product rule and chain rule. So if it's a product rule, this is u and this is v. And when you take the v prime, use chain rule. When you take the u prime, it's dy over dx, right? Because you need to write y with respect to x. And here too, x and y, you'll have to use the chain rule. Sorry, product rule. With all the plans there, u prime v plus v prime u. So u prime times v plus v prime. So derivative of the outside times derivative of the inside. Cosine 1 over y times derivative of the inside. Remember, inside it can be written as y power negative 1, right? And so the derivative of the inside would be negative 1, y power negative 2, right? Negative 1 minus 1. Where are we? So that's derivative of inside. And then you have the y itself that is in the inside, right? So that has to be dy over dx. That's v prime and then u. So times another y. All that for the left side equals the right side 0 minus u prime v, u prime v plus b prime v. Okay, we'll do a little cleanup here so we get to see it better. Minus, I bring the y in front, and this is y power negative 2 will become y squared cosine 1 over y dy over dx is equal to, on the other side I'll have negative y, I distribute the negative, minus x dy over dx. This is a little complicated just because of the y involved inside your chain rule, right? Because of the y involved there, you had to also remember to do the dy over dx, because ultimately you had to take the derivative of that y as well. So if it is not x, plain x, you'll have to go on with the derivative chain. Oh, no wonder it's called the chain rule, huh? All right, let's single out all the dy over. Okay, this one can cancel off, so let's do that. But I want to kind of circle all these terms. So technically, only this negative y is the only term that does not have the dy over dx. So we can keep that on the right side and move the x dy over dx, this negative x dy over dx, to the left. So it looks like this. Plus x dy over dx equals negative y. I moved the negative x dy over dx to the left by adding both sides by x dy over dx. All right. Now let's pull out or factor out the dy over dx. That gives us sine 1 over y minus 1 over y cosine 1 over y plus x equals negative y. Wow. Now we will have to divide both sides. So I don't want to show too many steps. So I hope you'll understand that we divide both sides by the sine 1 over y minus 1 over y, this whole expression, right? And so dy over dx is negative y all over Technically, that is your answer. However, you may be asked to simplify because of this one situation. What is that? That is that you have this 1 over y. Okay? They might say we want no fractional part in the denominator because it might appear as a complex fraction. It is a complex fraction in that sense. So for simplicity's sake and for complete simplification, what we have to do though is, for this, just because of the complex expression that we have here, I want to see that you do the LCD. Right, so if it's the LCD, y is the denominator, which is missing in the other places, right? So I'll have to do up and down by y because that's the LCD. Yes? And then Now they all have the same denominator y in the denominator. The denominator is y. We're only focusing on the denominator here, right? So that's going to be y times sine 1 over y minus cosine 1 over y plus xy. And then by complex fractions, you write the numerator as it is times the flip of the denominator. This whole thing is the denominator. So you have to flip it or to take the reciprocal of this. So that becomes negative y times, flip it. So it's going to be y over y sine 1 over y. Shove them all together. You get negative y squared over that is your dy over dx on this side. So although our problem kind of ended right here, I should say, right, this part here, because of that complex fraction situation, we had to simplify it by taking the LCD and then bring it out this way. Remember, this 1 over y is not a problem because it's part of the sine angle. So it's part of sine and cosine, so that is really not a problem. It can be a fraction because it's not a fraction inside the fraction. It's a fraction inside a trig function, which is fine. It's just that you can't have a fraction within a fraction, either the numerator or the denominator or both, in which case you have to clear it and just have one division bar so that there's a clear-cut numerator and a clear-cut denominator. For a change, let's try different variables, okay? Find dr over d theta. And this comes in polar coordinates, so theta and r are used there. And that's what's given to us. Yeah. It's not x and y, it's r and theta. And so we need to differentiate with respect to, it has to be this theta from the denominator with respect to theta. So theta is good. R is a function of theta. So wherever r is, you have to remember to do dr over d theta. And that's also the big clue because you're trying to find dr over d theta. That's going to be half theta, half minus 1. So for r also, it appears the same way, half minus 1. But remember, it's chain rule because of r. So dr over d theta equals 0. Half minus 1 is negative half. So by now, you should be familiar with the fact that I'm going to move it to the denominator. R power half. So move it to the denominator so that the variable is, the power is positive. Now I have to get dr over d theta by itself. So I subtract 1 over 2 theta power half on both sides. That goes away. Right? One last step. Of course, we have to clean up after that, but this means I have to get rid of this 1 over 2r power half on both sides. Remember, you can also think of the whole idea as multiplying both sides by the reciprocal of this. Same effect. But I wanted to do it this way for the explicit fact that you're dividing to remove it, and to also show you how we deal with complex fractions. We just did that problem, so that should come in handy now. So you always write the top fraction times the reciprocal of the bottom fraction. Right? And that will help us to cancel off the 2's combine them. Negative r power half over theta power half. And there are plenty of ways you can rewrite this in equivalent terms. So that's going to be negative r. I write the expression that we have here, which is the same as negative root r over root theta. Or, because they have the same, because they are like radicals, like radicals, we can bring them under the same radical. So any one of these options would work. Find d squared y over dx squared. That means the second derivative, x minus 1. From practice, we know that when we have the radical, we have to write it as a rational power, rational exponent, because that helps us to do the power rule. And now we're ready to differentiate with respect to x. When you do the differentiation the first time, you obviously get the first derivative. So 2 times half y power half minus 1 times, of course, remember the chain rule, dy over dx, because y is a derivative of x, equals derivative of x is 1 minus derivative of y is dy over dx. Now these go away. And that's going to be y power negative half, so it's going to be 1 over y power half dy over dx, 1 minus dy over dx. So the terms that contain dy over dx are being collected now. So I'm collecting them all on the left side, so it becomes 1 over y power half dy over dx plus dy over dx. So I add dy over dx on both sides. That leaves us with just the 1 on the right-hand side. Factor out the dy over dx. 1 over y power half plus 1 equals 1. I now have to divide both sides by 1 over by this expression, but before I do that, I want to simplify this. Make it into a single fraction, because you have two terms here. One is a fraction, one is not a fraction. The LCD is y power half, so it's going to be 1 plus y power half over y power half. I want to keep it as a half because I don't know if I will need to simplify it or combine it with something later. And so you can save till the end to convert it back to a radical. Divide both sides by this, so I get 1 over 1 plus y power half over y power half. Right? I'm slowly weeding you off of too many steps. So I want you to see that what I did was to get dy over dx, I divided both sides by this entire expression. You have a complex fraction. We've seen enough of these now, so we know what to do. Times y power half over dy over dx is y power half over 1 plus n. So, I can at this point do this, right? If this was the last step. But if you come back to the question said find d squared y over dx squared, which means we're not done. We've only found the first derivative. We need to find the second derivative. Therefore, I do not want to write it as a radical. I'll keep it as a power half because it's going to help me with the second derivative. Okay. So I'll just say here, this is the first derivative. We're asked to find the second derivative, so we go on. Second derivative would be d squared y over dx squared equals. Now you're taking the derivative on the right-hand side, and you have to see this as a quotient rule. So this has to be u and this has to be v. Okay. So u prime v minus v prime u all over v squared is what we have to do. And again, I don't want to take too many steps and make it look more complicated than what it is. So let's go ahead and do the u prime. U prime will be half y power negative half times dy over dx. U prime v is 1 plus y power half. U prime v minus v prime. V prime, that's going to be 0 plus the derivative of this. We just did the derivative here, right? It's going to be like this. V prime u all over v squared, so it's 1 plus y power half, the whole square. So just to kind of save space, let me put that information right on top here. Okay, that's better. Minus half. This also kind of goes down, so I'll put the y power half goes in front, and then this will be 2. Y power negative half goes to the bottom. And it's also not manageable. Let's go. Clearly, we see that this and this, they're the same, so they cancel off. And then we have dy over dx. That's common here. Pull that out. Even 2 is common, but let's just pull out the dy over dx. 1 plus y power half over 2y power half minus a half. Isn't it? That's all over 1 plus y power half, the whole squared. And on the left side, we had d squared y over dx squared. That's what we found now. And now it's time for us to replace the dy over dx by what we found here as the first derivative, right? Dy over dx is y power half over 1 plus y power half. Let's do that. So to kind of indicate that, this v is replaced there. Okay? So that they're all either in x and y, or in this case, it's all in terms of y. Okay, now let's try to distribute this inside, because that will simplify it. Again, I would like to save a step here, but because of the way it is, I think it'd be better for me to show. So I distributed for the first term, and then I have y power half over 1 plus y power half times 1 over 2. Quite obviously, because of all the product, this whole factor cancels over this whole factor, and this one goes away with this one. That went a little out of range for you. Let's see, d squared y over dx squared. This first term, everything cancelled except the 2, so it's going to be 1 over 2. And for the second term, I had a 1 over 2 times y power half over 1 plus y power half. all over 1 plus y power half the whole squared. Okay, now things are back in focus because he has simplified him. And now we want to see if you can simplify it further, because clearly you see it's a complex fraction because you see a fraction on the numerator. Okay, so my focus now is the numerator. They have 2 common, but you also need to get the LCD. So multiply up and down by 1 plus y power half. So again, I'll try to insert that information here. That's the LCD part there. And upon doing that, you get 1 plus y power half minus y power half all over 2 times 1 plus y power half all over 1 plus y power half the whole squared. I hope you're with me on this. Okay. Again, pause, do it on your own if you're getting confused, and then you'll see that it's all working out fine. Okay, I'm taking the LCD for the numerator alone. Okay, I'm not touching the denominator. Okay, this move has helped us because this goes away. You still have a fraction in the numerator divided by this denominator. So we have the complex fraction here, where the numerator, as it is, times, there is a 1 underneath this. So flip off the denominator, which would be 1 over 1 plus y power half the whole square, which basically is 1 over. So this is a power 1 and that's a power 2. So they add the powers by exponent rule. And we get whole cubed. Okay. D squared y over dx squared. At this point, if you want, you could come back here and say 1 plus square root of y, the whole cubed, because your original question had the radical and not the power. Okay, and so that is our answer. And what the other problem types you might see is to do the implicit differentiation and then find the equation of the tangent line, okay, for a particular point. So say, for instance, you're given 2y squared minus 3y plus 11 equals 2x squared plus x. And say, use implicit differentiation to find the equation of the tangent line. At 2, 1, let's say. So if you have something like this, well, you do know that you have to find the, so it's the same idea, slope point form that we did for the equation of a tangent line. Slope point form, we have the point, we need to find the slope. To find the slope, we need the dy over dx, the derivative. Because of the implicit nature of this expression, you'll have to do the 2 times 2y dy over dx minus 3 times dy over dx plus 0 for the 11 equals 2 times 2x plus 1. The derivative of the right-hand side were all x's, so no problem there. And so that's going to be 4y dy over dx minus 3 dy over dx equals 4x plus 1. Pull out the dy over dx. And then one more step, do the dy over dx. Divide both sides by 4y minus 3. That gives us 4x plus 1 over 4y minus 3. Typically, we stopped here, but this question, they gave us a point, and they also told us to find the equation of that line, the tangent line. So then we have to do dy over dx at, the given point was 2, 1. Yeah, 2, 1. So it's 2, 1. X is 2 and Y is 1. Plug that in. That comes out to be 9. And so you have the slope and a point. So Y minus Y1 equals n times X minus X1. Y minus 1, Y1 is 1, n is 9, X minus 2 for the X. X1. Y minus 1, 9X minus 18. Add 1 on both sides. 9X minus 17. And that's your answer. So this theme will come along all along, where once you find the derivative, you might be asked to find the equation of a tangent line, or sometimes they'll just ask for the derivative. Okay? So just go for it as per the question. And with that, we'll come to the end of this particular section on implicit differentiation. I'll see you soon in the next video.